And a very happy Tuesday evening to you all. It's a great night for a ham radio class. It's not a night fit for man nor beast outside here in upstate of South Carolina. We've got heavy rain coming in. You may hear it on the roof as we go along. But we're going to be talking about an amateur radio extra class topic, one that's high on all hams list, antennas and transmission lines, or feed lines as they're also known. I'm Gary, ham radio call sign Whiskey 4 Echo Echo Yankee, and I'll be your instructor tonight. And tonight we're going to take the first half of Chapter 9 from this book, the American Radio Relay League Extra Class License Manual, 13th edition. So this is the book that we use, and if you want to upgrade from your general class or advanced class license, please come along with us and partake. So if you've been following along with us in the class, you know that we had Hurricane Helene come through South Carolina not too long ago, and it put us back by about 3 weeks for this class. 2 weeks because of the hurricane, and then another week because of internet troubles. So Bruce, if you take the laptop for a second, this is the schedule that we're on right now. Tonight is part 1 of antennas and feed lines. Then next week we'll conclude the rest of Chapter 9. Then that was to be the end of the class or thereabouts, but we're going to take a break at that point because Christmas and New Year's, and the plan is to come back in January, January 7th, for Dave's excellent presentation on topics in radio propagation. I can't recommend it more highly. It's something that even if you get your extra class license, you want to come back and watch that. And then we'll have safety and practice test on January the 14th, and then our last class, very last class, will be practice tests together on the 21st of January. And we will have then, starting in February, I don't have the dates up yet, but a general class and another technician class. So if you know of anyone who's looking to get their ham radio license, just give them my email address and have them contact me. Or if someone is upgrading from technician to general, we'll have a new live class so people can participate in the Zoom classroom. So that's the housekeeping for tonight. Let's go ahead and get started. Before we actually talk about the chapter topics, I have a little introduction or some things. My whole point is I'm trying to maybe plant some seeds for you to think about, and think about some things with antennas in a new way. If you remember, we talked about impedance. That's the combination of resistance and a reactance. The reactance could be inductive reactance, or it could be capacitive reactance. They could be in series or in parallel. It becomes a complex situation there that is noted either with a magnitude and phase, or with a number that has a real and imaginary part. So that's impedance. That's the combination of resistance and reactance. And you can plot, if you do the math on a Cartesian plane here. Let me turn on my laser pointer. All right, there we go. So this is the real axis on the x-axis. Real resistance is here, inductive reactance is up there, and capacitive reactance negative. So you might remember that we talked about that. We're going to talk a lot more about this next week, so stay tuned for that. Ohm's law, we learned this in the technician class, of course, E, I, and R. And Ohm's law applies to DC circuits and AC circuits when you have a resistance. But there is such a concept, and this is more concept than reality, Ohm's law for impedance. And it has to do with the fact that you can plug the Z in for the R in the Ohm's law pyramid. Now, it's not strictly true unless there is no reactance, or reactance is 0. But the thing I want to point out is that impedance can also be looked at as a ratio of voltage to current. And in an impedance, the voltage and current may not be in phase, but note this ratio. So if you can just keep that in mind, that the ratio of voltage to current in a circuit has to do with the circuit's impedance. And lower voltage, higher current means it's a lower impedance. Higher voltage, lower current means it's a high impedance or a higher impedance. And this is actually demonstrated by our old friend, the half-wave dipole antenna. When we feed it at the center with the low impedance coax, 50 ohm coax, this is the low impedance point of the antenna, which means this is the place where maximum current is located on the antenna, which kind of makes sense because as you go out toward the end, there's no place for current to go, so this is the high voltage part of the antenna. You can look at it here in another way as the cycles move around. Well, let's look at it dynamically. So the blue is the current, and you can see the current maximum is going up and down as the RF AC wave is occurring. So this here in the center is the low impedance point of the antenna. Out here we have voltage swinging to maximum plus or minus with very little current. Notice the current is, so this is a high impedance point. The reason I say is you can actually chart the impedance along a half-wave dipole antenna, the center being the lowest impedance point, the outer points being the highest impedance, and somewhere in here some magic can happen. We'll talk more about that as we come up, but I just wanted to plant that seed of impedance being thought of as the ratio of voltage to current. And I will caveat that we're going to talk about antennas and feed lines over 2 weeks. This is such a deep subject, however, and we're only going to be able to skim the surface to give you a little bit of information about it. Also, the other thing is I'm not an engineer. I'm not going to give you Maxwell's equations. I'm not going to talk about wave fronts and wave theory, a little bit maybe next week. So what you're going to hear is from a technician's point of view, meaning an electronic technician, what antennas and feed lines mean to me. So let's get it all started with the old standby, the isotropic radiator, also known as a point source antenna. It's theoretical. You can't build it, but it's a concept that those engineers use, when they're doing their designs. It's got a center point where energy is being radiated equally out in all directions, and there are no reflections. There's nothing to inhibit it. So this is an isotropic radiator. It's a reference antenna. The more common antenna that we're going to see is a dipole antenna. And here we're looking at a side view. So here's the center of the dipole antenna. Here's at the end of the dipole and the other end of the dipole. And in free space, the output of the antenna is kind of egg-shaped with nulls at the ends. Well, okay, we're not in free space. We're on the Earth. We have, ground below us and other things around us which reflect. So when you add the Earth under a dipole antenna, the egg shape kind of flattens out. And so this is the kind of pattern that you get from a dipole antenna over real ground. And you can look at it above, looking from overhead. You can see the pattern here. The nulls aren't quite as distinct anymore, but they do go down at the end. And we can look at it on the side, and you can see that it's got lobes of energy that come up from the antenna and out. We're going to talk a lot more about that as we go ahead. But in comparing the dipole antenna to an isotropic radiator, we say that a dipole has 2.15 dB of gain over an isotropic radiator in its major lobe, or right here, for example. So if the dipole antenna is going back and forth here, the broadside to that this is where it's got some additional gain in this direction. The isotropic, being the circle down below. Again, remember that the center-fed dipole's impedance is lowest at the center and does, well, I guess I put it down there. The nominal impedance of a dipole antenna is 73 ohms. And that gives it a good match to 50 ohm coaxial cable. But something that many people didn't know, and I think this is probably one of the more important slides in this presentation, is the fact that a dipole antenna's impedance varies with the height above ground. So what we're looking at over on the left-hand side here, the vertical scale, is the resistance of the antenna in ohms. And here we're looking at the height in wavelengths above the ground. So here's one wavelength. So if it was a 20-meter antenna, this would be 20 meters above the ground. And you notice that when you start out low to the ground, the antenna's impedance is not 73 ohms. It's like 10 ohms. And as you come up high and higher and higher, okay, there's 73 ohms. Or it even goes, as you go higher, it goes above. What you're seeing here is that it's regressing to a mean, or the mean or average impedance of a dipole antenna is 73 ohms, but it all depends on how high you are above the ground. So I tell people that hey, I'm not getting a good antenna match to my dipole, do I need to lengthen it or shorten it? I tell people, well, try changing its height. And see if you get a little better match that way. It really can have a major impact. So an antenna's impedance varies with height. It's one of the factors. It also impacts the antenna's angle of radiation. For DX work, sending signals out to the ionosphere a long way away, we want a low angle of radiation to go out as far as we possibly can. Higher angles of radiation will go up and bounce down shorter distances. So higher antennas are generally better for DX. And also remember that an antenna is kind of reciprocal for transmit and receive. So if you get improvements on transmit gain, you're also going to get improvements on receive gain as well. All right, I've always said I was going to do this, but I never have done it. So here we are. I'm going to give you a balloon analogy, and I have my sample balloon over. Whoa, I just dropped it. Let's go over to the green screen, Bruce, if you don't mind. He didn't know I was going to do this, so. So here is our balloon, analogous to, let's say, 100 watts of radio frequency energy. The air inside the balloon is analogous to 100 watts of air molecules. Okay, there is no such unit, but okay. And that's what's inside the balloon. If we can control the shape of the balloon, if I can compress the balloon out, you see how it squeezes out left and right there? It goes farther. It has higher gain in those directions. Whereas up above, where my hand is here, it has less gain. You don't get something for nothing. But if we can control the pattern of the output of the antenna, we can get gain in certain directions. Now, we started out with 100 watts of air molecules, my imaginary unit. When I squeeze it, we still have 100 watts of air molecules. They're just going in slightly different directions. Which leads me to this trick question. You take the laptop. So how does the total amount of radiation emitted by a directional gain antenna compare with the total amount of radiation emitted from an isotropic antenna, assuming each is driven by the same amount of power? What do you think? It's the same. It's still that 100 watts of air molecules, no matter which shape you have there. The same power density level is in either of the two. All right. When we're compressing that balloon of the pattern of an antenna. We are controlling various phasing and things that's going on in the antenna. And we have something called the near and the far fields. The near field is where the antenna is located, and it's where there's interaction going on between elements in the antenna. And we're starting to build the pattern of the antenna, but you cannot make measurements in the near field. It's a confusing area. That's this area right in here. This is the near field where all of this interference is happening. I heard this, that it's typical 10 wavelengths away from an antenna is where the start of the far field exists. And the far field is where the antenna's pattern is independent of distance. It's formed itself. Dave Kassler in his videos used to slide something like this, where he talks about with a dipole antenna, and you look at that and you have constant current through an infinite number of points going out on the dipole, and they interfere with each other. There's a confused area here, the near field, but as it comes together, then you can see the pattern is formed. That is the far field, and that's how we can get constructive and deconstructive interference in an antenna, and that's how we get the patterning coming of the signal coming from the antenna. So antenna feed point impedance, we said that antenna height definitely impacts that. Conductor length will also impact the antenna feed point impedance. Conductor diameter, larger diameter wire, or if you can build a cage of wires, it will give you more bandwidth and will affect the feed point impedance. Also, nearby conductive objects can impact feed point impedance. A characteristic of feed point impedance is, and with antennas, has to do with the Q factor, the Q of the antenna. That's how broad the bandwidth is of the antenna to meet a certain requirement. We always in ham radio talk about standing wave ratio bandwidth. Hams typically want an SWR bandwidth below 2:1. Your solid state transmitter is going to be happy with that. It'll put out its full power without doing any adjustments. And so the Q of an antenna, here is a low Q antenna. Here's the 20 meter band, 14 megahertz. And you can see it covers most all of the band below 2:1. So this is a low Q, low reactance antenna. There's a radiation resistance, but not a lot of reactance going on this antenna. A mobile antenna, on the other hand, something you might put on your car, is going to be very reactive. It's going to have a coil. And so the bandwidth of that antenna is going to be much, much narrower. That's a high Q antenna. So the Q of an antenna is a measure of the SWR bandwidth relative to the center frequency of the bandwidth. So here's the center frequency for this, and here's the center frequency for this, and then you can see the bandwidth here is much, much less. And bandwidth is the frequency range over which an antenna satisfies a performance requirement. And I set the performance requirement to be SWR below 2:1. Because that's what makes solid state transmitters happy. And below the resonant frequency, the antenna is said to be capacitive. Above the resonant frequency, the antenna impedance is said to be inductive. Inductive reactance is happening here. Capacitive reactance is happening here below the resonant frequency of the antenna. So I want to introduce you to the concept of good and bad. In this case, good R versus bad R. Good R is what we want. It's the radiation resistance of an antenna. It's the part of the antenna that does work. And I stole this diagram from an Indian ham. I've given the URL down below, so the spelling is his, but okay. Radiation resistance. This is the good R. This is the part of an antenna that is going to dissipate real power and radiate it out into space. We want to optimize good R. We want radiation resistance. We have capacitive reactance, okay, and remember we have inductive reactance. Remember, reactances don't do any work. They're just storing energy either in a magnetic field or an electrostatic field. And then the new concept is bad R, or ohmic resistance. And ohmic resistance can be as severe as this. You've got corrosion on your antenna, and so it becomes a resistor more than it does a connection. So that's bad R. That's a resistance in the circuit that's only going to generate heat when you apply RF energy. It's not going to radiate any energy. Back to our mobile antenna, you remember that high Q, low bandwidth antenna? Well, here's an example of one on the back of a pickup truck. And here we want to have the wire diameter to be as large as possible in the inductor, because all of the resistance of that wire is bad R. It's just going to heat up the coil. It's not going to radiate energy. So always we're thinking, radiation resistance, it's the good R, and its definition is the value of resistance that would dissipate the same amount of power as that radiated from the antenna. And antenna efficiency can be measured using this. Radiation resistance, the good R, divided by total resistance, the good R plus the bad R, in a percentage, gives you the antenna's efficiency. So good R, the radiation resistance, that's what we want. Bad R, losses, we don't want that. And so the higher the ohmic losses are in your antenna, the less efficient the antenna is going to be. We're not going to talk much about it this week. We'll talk a lot more next week, though, about then something else that I'll throw in here. Here's the good R, radiation resistance. Here's the bad R, and then here's reactive power that is reflecting power back to the source. We're going to talk more about that next week. We've talked about the half-wave dipole. I always hold my hands out like this when we're talking about it. But if you turn it on its side, you get the quarter-wave vertical, with a quarter-wave element going up into the air, and the element that would be going down into the ground is actually replaced by radial or conductive ground wires down below it. So this is a quarter-wave vertical antenna. Good for DX because it has a very low angle of radiation. So that's helpful. So how do you improve the efficiency of a quarter-wave vertical antenna? By adding radials. More wires. So this is from DX Engineering, I believe. It's their radial plate. So what you do is you have your vertical antenna mounted through here, and these are locations where they want you to connect ground wires, radial wires to. In broadcasting, they want to have them every 1 degree or every 2 degrees. So that's 360 or 180 radials. Whoa! Well, you don't have to do that for amateur radio. And in fact, when we went to the W4DXCC convention a few years ago, a gentleman did a paper and talked about it. And the optimum number for amateur radio operators is 38. If you can put 38 radials down, you're going to be within 1 dB of having 180 radials. So that is the optimum number. And the radials serve a purpose. It gives the antenna a way to radiate the RF energy. And I likened it to, in previous classes, if you've ever been in a swimming pool, especially if you've done competitive racing, and they teach you the special way to do this is you're coming up to the wall of the pool and you flip yourself around and you kick yourself off the wall of the pool and you keep going back in the other direction. Well, in this case, the swimmer is the electromagnetic wave trying to launch itself from the vertical antenna, and the radials are the wall of the pool that gives it something to kick against. Without the radials, it's not very effective. I'm going to tell a story on myself here in just a second. What about ground rods? Couldn't I just use a ground rod instead of radials? Well, ground rods are great as an RF ground for the ham shack. Yeah, okay. For lightning protection, yes, yes, yes. But for antennas, well, it's better than nothing, but it's a poor substitute. When I was first licensed as a ham back in 1969 as a novice, call sign WN8GAJ, I didn't know anything really about radio at that time, and my dad, God bless him, he didn't either, but he helped me. And so what we did is we put up my first antenna. It was a high gain 18V vertical antenna. It had a coil down at the bottom that you could tune to match the antenna on 80, 40, 20, 15, or 10, one at a time. It was not a multi-band antenna. And it needs radials in order for it to perform. We didn't know that. It just said it had to be grounded. So we pounded a 8-foot ground rod into the ground and let it go at that. I didn't have the best signal, let's put it that way. And it was only years later that I went, oh, that's what we should have done. So don't be like me back in the day. If you can, locate your QTH near salt water, because then if you put up a vertical antenna, verticals love salt water, not fresh water, salt water, because what it does is it reduces the angle of radiation from the antenna down even further. And by doing that, you get your signal to go out farther to the ionosphere and a longer distance for the same amount of power. So the low angle radiation increases. Low angle radiation increases when you are adjacent to salt water. And with DXpeditions that go to the Pacific, for example, they'll set up their antennas right on the beach for this very reason. Now, soil conductivity has a major impact on antenna efficiency, especially vertical antennas. And where we are here in the upstate of South Carolina, we have pretty poor soil conductivity. Here's a map of the United States. The black regions have great soil conductivity. The other regions, not so much. So this is going to be a factor that you have to consider if you're going to be putting an antenna up. Verticals over poor ground with poor soil conductivity have a higher angle of radiation. So what we're seeing here is, here's perfect out to the reference line, the 0 line here. All right, got good soil conductivity. Okay, well, it's not as much gain, but okay, it's about in the same spot. Very poor, oh, the angle of elevation starts going up, and so you don't get the same performance depending on the soil conductivity. If you've got good soil conductivity, you'll get better performance than poor. Remember we talked about the isotropic antenna and the dipole antenna, and we talked about the antenna gain. Just keep in mind, this is the number you need to know, 2.15 dB, that a dipole antenna has gain over an isotropic in this major lobe direction. And if you're making comparisons, if you're going to buy an antenna, take a look at what the manufacturer has done. Are they referencing the gain of their antenna to a dipole or to an isotropic antenna? You have to make an adjustment by 2.15 dB if one manufacturer is using one standard and the other manufacturer is using another. So just keep that in mind. And as I mentioned before, we don't get something for nothing, so more gain equals a narrower beam width. So you've got to make sure that, okay, if you've got a gain antenna, you have to figure out a way to point it. That's where antenna rotators come in, that you have to make sure that you can rotate the antenna in the direction. If you want to go toward Europe, well, you better be at 30 to 45 degrees from here, because if you're pointed 270 degrees, they won't hear you. Also, an antenna with higher gain, narrower beam width, is harder to use in a contest sometimes. Sometimes a 2-element antenna is better. It has a wider beam width, but you don't have to keep moving the antenna all the time. And they wanted us to know how to measure the beam width of an antenna. So here we have a polar plot looking down on an antenna. And they're going to ask us, what is the 3 dB, or the half power beam width of this antenna? So we have to know how to read this graph. So the outer line is the 0 reference, and so that's where the maximum gain point is positioned right here. All right, and if we look at the legend here, this is minus 3 dB, minus 6 dB, minus 12 dB. So the minus 3 dB point, if we go back over here, okay, it's right about there. And in the opposite direction, it's right about here. So between these 2 points, we can look and see, so there's 30 degrees there, there's 30 degrees there, it's less than that. We're going to guesstimate that in this case, the 3 dB beam width for this antenna is about 50 degrees. You can also use the same graph to indicate the front to back ratio of the antenna. So similar plot here. We've got the major lobe on the 0 line out here. That's what this outer line is here. And notice we have the decibels indicated here, minus 3, minus 6, minus 12. This is the front. This is the forward direction. This is the back. This is the reverse direction, and we can see that this is located between the minus 12 and the minus 24 line. So I'm guesstimating here at about an 18 dB front to back ratio for this antenna. We're looking down on top of this antenna in this case. You don't have to look down on top. What if you were looking at the side of the antenna? That's what this is. This is an elevation plot of an antenna, and we talk about an antenna having a major lobe from the antenna. Well, that's this one right here. It's on the 0 line, again, the outer line. But this antenna has a second lobe, a third lobe, and even a fourth lobe. And these are all at different angles of radiation up to the ionosphere. Now for DX, we say that we want low angle of radiation, so this is the one that's going to be most interesting to us. But a question would be, well, how many lobes are there in the forward direction? 4. 1, 2, 3, 4. So in this case, there are 4 lobes. And what is the front to back ratio of this antenna? Well, you can do the same thing. Okay, the major lobe is on the 0 line here. Here was minus 10, here's minus 20, minus 30. If we go whipping around over here, we can see that the back is going to be at around minus 30. So we're going to say the 30 dB front to back ratio for this antenna from this elevation diagram. All right, going back to looking from the top again, you can also look at the front to side ratio in the same way. Side ratio is going to be 90 degrees from the main lobe. So here's the main lobe on the 0 line. Here's minus 12, there's minus 24. We're going to say maybe 14 dB front to side. These are all parameters that you'll find the manufacturer may provide you and may help you in your decision if you're going to be looking to buy a new antenna. You might want to know what the manufacturer has measured from their antenna. Some of these are measurements, some of these will be computer calculations for the antenna as well. And again, what is the elevation angle of the main lobe? Well, okay, let's look at this thing, all right. Here's the main lobe. Here's 0 degrees. Here's 30 degrees, so that means this has got to be 15 degrees. This has got to be about halfway between, so this is going to say 7.5 degrees. That's how we calculated the elevation angle of the peak or main lobe using this diagram. Why did we do all that? Well, because there's test questions. So that's what we're doing. We mentioned that if you can put your vertical antenna near salt water, that's going to enhance performance. Well, if you can put a vertical or a dipole antenna on a hillside with the downward slope going toward the place that you want to communicate with, that's going to help you. An elevation angle decreases along a downward slope, which is another way of saying the low angle radiation increases if you have a downward slope. It's better for working certain DX stations that are far away. And if you buy the antenna handbook from the American Radio Relay League, you'll be given access to a program called High Frequency Terrain Analysis. And you can actually get topographic lines for your location, where your station is, using this URL that we have down here from K6TU. He's got an automated system that he'll generate 360-degree plots from your QTH. And then HFTA, one of the things that you can do is you can plot your antenna, set it up with a certain height and a certain amount of gain. Red here represents flat ground, and the blue represents the kind of gain that you might get at your location. Here's the angle of radiation, the lowest angle here and higher angles here. This location where this person is going to have much greater gain over flat ground because of their QTH. I know hams who won't buy a piece of property until they run HFTA on that property, and they ascertain, is this going to be a good place for me to set up a station? In my own case, if you want to come back to me just for a second, Bruce, I used to have a house in the northwest corner of Greenville County, and I could never work into Japan or Southeast Asia. It was really terrible. And when I ran HFTA, I bought the property before. When I ran HFTA, the highest mountain in South Carolina is Sassafras Mountain, right between my property and Japan. And that was causing me the opposite of what you just saw. That was causing me a loss of low angle signals coming from Japan. So HFTA can be your friend. The height of your tri-bander also, we said that higher antennas have lower takeoff angles. So if your antenna is low to the ground, even if it's a gain antenna like a tri-bander, it's going to be not as good for DX. You want to get it up as high as you reasonably can. All right, here's a topic near and dear to hams: budgeting. No, I'm not talking about budgeting for that new radio that you want to buy, although I've got my eye on one right now, as the guys over here know. We're talking about budgeting for telecommunications. And I like to say that ham radio operators are opportunists. We take advantage of good conditions. When the solar conditions are just right and we can get high frequency signals around the world with very low power, that's what we do. We love that. Telecommunications operators, on the other hand, are all about reliability. And so when they're creating plans for a circuit between 2 points, they create a signal power budget that ensures that a signal will get through most of the time, if not all of the time. So that's a telecommunications link budget. And that's what we're talking about here. So a dedicated radio circuit between 2 points can be called a link. It could be UHF or microwave. It could be a satellite circuit with hops to and from satellites. Or back in the day, before we had satellites at VOA, where I worked for 20 years, they used shortwave high-frequency radio to relay programming. And so they needed to know what the link budget was between 2 points so that they could get programs from the United States to an overseas transmitting station. You might remember we talked about in the measurement section, we talked about dBm and the power levels above 1 milliwatt. So here are some various levels. Bruce, you can take me out of the screen there so that they can see. 40 dBm is 10 watts, 30 dBm is 1 watt, 20 dBm is 100 milliwatts. And then conversely, below 1 milliwatt, minus 10, minus 20, minus 30, link power budgets are done in dBm. And I also want you to know there was an error in the book. We have a first printing book on page 9-7. 40 dBm is equal to 10 watts. They say it's 100 watts. That's not. It's equal to 10 watts. And they've acknowledged that. So, all right, knowing what we know, let's create a link budget. And to do that, we look at the transmit side and we look at the receive side as well. So we need to know the transmitter power in dBm. We want to know the transmitter's antenna gain in dBm. We want to know the path loss between the 2 points in dB. And then we want to know the receive antenna gain in dB. So these are all the things that factor into the budget. And you can put path loss on either the receive or the transmit side. I just put it on the transmit side. So in this case, if we have a calculated transmit power of 40 dBm, or 10 watts, we have a transmitter antenna gain of 6 dB, but we have a path loss of minus 100 dB, then we have a receive gain of 3 dB. Okay, the math is not hard. It's just adding and subtracting. And in this case, we come up with a sum of minus 51 dBm. So that's going to show up right around in this range right in here, minus 51 dBm. Is that enough? Well, it depends on your receiver and what you're doing. So again, on the transmit side, these are the things that we're looking for. And on the receive side, and here's where the receiver comes into play, the receiver's minimum discernible signal. Where is it that it can just barely receive a signal? And then what is your desired signal to noise ratio above that? And then you look at the entire circuit and see if you've got any additional margin in that circuit. So if we use the example on page 9-7, example 9-4, we have a transmitter power of plus 40 dBm, antenna gain plus 10, cable loss minus 3, and a path loss of minus 136, sorry. So the sum of this is minus 89 dBm. On the receive side, we have a minimum discernible signal in the receiver of 103, but we want a 6 dB signal to noise ratio at least. So if we take that away, then plus 6 and minus 103 gives us minus 97 dBm on the receive side. And we look at those two together, the transmit side is going to be able to give you minus 89 dBm. The receiver wants to see at least minus 97. Note that this is a bigger signal than this is, because minus. So the difference between the two is 8 dB. That is the fade margin of this circuit. That's what you use a link budget to determine, how much can the signal fade before you're going to have an outage. And remember, the telecommunications guys are all about reliability. That was a lot. Let's see how much we retained. Let's answer some questions. So when you know the answer, you can go ahead and unmute. What is the link margin in a system, okay, with a transmit power level of 10 watts, system gain of 10 dB, cable loss of 3, path loss of 136, receiver minimum discernible signal of minus 103, and the required signal to noise ratio of 6 dB? We just did that. Do you remember? What's the margin?
Charlie.
Yes, Charlie, 8 dB. But that's how we got there. I wanted you to see how we got there. So what is the received signal level with a transmit power of 10 watts plus 40 dBm, a transmit antenna gain of 6, receive antenna gain of 3, and a path loss of 100? When you put all those together, you do the addition and subtraction, you end up with, I'll help you out. Yeah, it's alpha, minus 51 dBm. So what is an isotropic radiator?
Charlie.
Charlie, yes. It's a hypothetical lossless antenna having equal radiation intensity in all directions, used as a reference for antenna gain. And which of the following factors affect the feed point impedance of an antenna?
Bravo.
Yeah, antenna height. And what is antenna efficiency?
Charlie.
Not Charlie.
Not Charlie. Okay.
Other way around. You're on the right track.
Bravo.
Bravo. It's good R, radiation resistance, divided by good R plus bad R. So a perfect would be 1. That'd be 100% efficient. So if you had no bad R, it'd be radiation resistance divided by radiation resistance. Great. But there's always going to be some bad R, so that's going to decrease the antenna efficiency. But you're on the right track. So which of the following improves the efficiency of a ground-mounted quarter-wave vertical antenna?
Alpha.
Yeah, you want that radial system, that ground radial system. And which of the following determines ground losses for a ground-mounted vertical antenna operating on HF?
Charlie.
It's not so good here in South Carolina. Soil conductivity. And how much gain does an antenna have compared to a half wavelength dipole if it has 6 dB gain over an isotropic?
Alpha.
The number I wanted you to remember was 2.15. So you get 6 dB minus 2.15 gives you a 3.85 dB. That's how you can do the comparisons. All right, what is the 3 dB beam width of the antenna radiation pattern shown? Do you remember?
Bravo.
It is 50 degrees. Here's 30, here's 30, here's the 3 dB point. It's going to be less than that, so 50 degrees. And what is the front to back ratio of this antenna?
Delta.
Yes, it's about 18 dB. It's between the minus 12 and the minus 24. All right, what is the front to side ratio of this antenna?
Delta.
Yes, it's about 14 dB. And what is the front to back ratio of this antenna? I heard somebody say B. That is correct. Here's the 30 dB line. If you go over there, it's a little further than that, and there's the 20 dB line. So it's between 20 and 30, yep, 28. Yep, good. All right, what type of antenna pattern is shown?
Alpha.
Yes, this is what is known as an elevation pattern. We're looking at the side of the antenna. And what is the elevation angle of peak response in this antenna?
Charlie.
Charlie, 7.5 degrees. Here's 30 degrees, so halfway from, that's 15, halfway is 7.5. What is the difference in radiated power between a lossless antenna with gain and an isotropic radiator driven by the same power?
Charlie.
Yeah, they are the same. And they just go in different directions. What is the far field of an antenna?
Delta.
Yes, by definition, it's the region where the shape of the radiation pattern no longer varies with distance, usually about 10 wavelengths out. So how is the far field elevation pattern of a vertically polarized antenna affected by being mounted over seawater? Not alpha.
Delta.
Delta. Radiation at low angles for the good DX increases. We have more power going at lower angle. Radiation at low angles increases. And how does the radiation pattern of a horizontally polarized antenna vary with increasing height above ground? Talking about radiation pattern.
Baker.
Not Baker.
Takeoff angle of the lowest elevation lobe decreases.
It's actually alpha. It's the takeoff angle of the lowest elevation lobe increases. Is that right?
It's actually Baker in the book.
Yeah, I was going to say, why did I do that? All right, point off for the instructor. I have to look at that one. Yikes. Good. Sorry about that. How does the radiation pattern of a horizontally polarized antenna mounted above a long slope compare with the same antenna mounted above flat ground? Let's see if I got this one right.
Let's try Baker again.
Yeah, Baker.
The main lobe takeoff angle, the angle, decreases in the downhill direction. That is correct. Yeah. All right. What happens is the Q of an antenna increases. When the Q goes up,
Baker.
Baker.
yes, SWR bandwidth will go down. And that, ladies and gentlemen, is the end of section 9.1. You are here for a well-earned 5-minute intermission. So go ahead and get up, move around, stretch, get something to drink, and come on back, and we'll do section 9.2 together. Well, I want to thank you all for joining us tonight. We actually, I looked at the chat on YouTube. We have participants from Germany and Belgium tonight, so thank you for tuning in. Appreciate it very much. I'll have to look into that mistake I made. Maybe I've got another one coming up tonight. I make my own slides, so I can only blame myself. And for those, you might know, if you've been following along with us, we have a Zoom classroom with students, and then also we have the YouTube live stream. And for the Zoom classroom, I won't say anybody's name, but his initials are Dave, didn't spotlight me. So it was hard for people to read the slides. But okay, we've corrected that problem too. It's the rain. I blame the rain. All right, so let's get started on section 9.2, practical antennas. But first, I want to point out something that is really probably more important than the type of antenna that you select. And it's something we've already talked about before, and that's location, location, location. The location of your station really can have a great bearing on how well it gets out. And the perfect location is on an island surrounded by salt water on top of a mountain with downward slopes going in all directions. Okay, good luck with that, especially getting internet coverage there. But okay, well, with Starlink, I guess you could do it. All right, so that's one thing. Location is important, and RF noise, I contend, is probably another important consideration. We have note that for HF propagation, that signals come in at various angles, and the more distant signals typically come in at lower angles of radiation. And we saw earlier tonight the high-frequency terrain analysis. One thing I didn't have on the original slide, which I've added here, are something that the ARRL includes, which are the 11-year sunspot DX statistics for different locations, Europe, Japan, the Pacific, and these are how statistically signals come in at what angles of radiation, from 2 degrees, 4 degrees, 6 degrees, from this particular direction. In this case, the blue is flat ground, and the red is your location, as plotted by HFTA. Note the high gain for these low angle things that flat ground would have a hard time capturing. So that's why HFTA is really a godsend in determining a good location for your ham radio station. Now, okay, if you're already there and you're not moving, all right, but you can still run HFTA and get some insight as to what's going on around you. The other thing I contend is RF noise is a major issue. Here's a YouTube video on finding RF noise. It can be any sort of thing that affects you, but by and large, I find these guys. The lightweight wall warts, the DC power supplies, are great high-frequency noise generators. So if you can do an exorcism, if you can remove them from your house, from your ham shack, you'll go a long way into reducing your noise. All right, that was my sidebar. Now back to our regularly scheduled program. Half-wave dipole, that's where we started. Do you remember the formula in feet? For those in Europe who are doing a metric, I don't know your formula, but for us it's 468 divided by the frequency in megahertz will give you the length of the antenna in feet. And we say that an antenna that is too short is said to be capacitive. And it relates to the phase angle of the voltage to current along the antenna. If we remember in the general class we talked about Eli the Iceman, ELI, voltage leading current for inductors, Eli, or ice, current leading voltage. Well, that's what we mean here, is that a dipole, when it's too short, it's going to be capacitive. A dipole that's too long is said to be inductive. Again, the ratio of current to voltage are going to be out of phase. The voltage is going to be leading the current. All right, but Gary, I've only got a limited amount of space in my backyard where I can put up an antenna. Okay, you can shorten an antenna, and you can do that by adding loading coils. That's one way for a horizontal dipole antenna. If you put loading coils in the radiating elements here and here, and make sure that it's balanced, then what you're going to do is decrease the actual physical length of that antenna. It won't be 468 divided by the frequency in megahertz anymore. It'll be something less. However, you don't get something for nothing. The Q of the antenna goes up, which means the SWR bandwidth goes down. Trapped antennas are interesting. Traps are low-pass filters. And so what happens is here we have a tri-band dipole. The longer sections are going to be for the lower frequencies. So let's say here's 14 megahertz. That's going to be using all of the antenna out to the insulator from here out to here. 15 meters might only go out to here to here. 10 meters is only going to be using, from here, see there's 28 megahertz, to here. But note, 14 megahertz times 2 is 28 megahertz. So this antenna may radiate harmonics. So if you've got a transmitter that has a strong second harmonic output, it'd be misadjusted or some problem with it, well, this antenna would radiate it. So that's just something to know about trapped antennas, is they can radiate harmonics. Also, fan dipole antennas may also radiate harmonics. There's no harmonic suppression in the antenna. We're talking about practical antennas now, so I just want to give you these things here to be considered. A folded dipole antenna, we say you make it with 300 ohm twin lead and you feed it with 300 ohm twin lead. It's a half wave dipole antenna, or at least the length is the same out to the end, but then remember, this is twin lead. This is 300 ohm twin lead. Do you remember back in the day when we used to receive TV off the air, the old analog TV, and you had the line coming down, it was flat and they had 2 wires in it? That's what we're talking about here. You short the 2 wires out at each end, and this becomes a 1 wavelength long loop. Half a wavelength and another half of a wavelength. It's a very thin 1 wavelength loop. It has a 300 ohm input impedance, and that's why if you feed it with 300 ohms as well, you'll have low losses on the feed line, and then you can use a transformer, RF transformer, or some other means to impedance match to your transmitter in the ham shack. This is a folded dipole antenna, impedance 300 ohms. An antenna that's popular with some hams, and some hams swear at it, is the G5RV, invented by a British ham. It's a multi-band dipole antenna. You are going to have to use an antenna tuner. It's fed from the transmitter with coax to a one-to-one balun, a current choke, to a section of open wire line, and then on to the antenna. The G5RV, it's a fixed length antenna, 102 feet. This says it's 80 through 10. I've never used a G5RV. Have you guys ever used a G5RV? No, I'm getting shakes of the head. But just know that it exists. And this is how you can identify it, because it goes through all these various permutations with a coax to a one-to-one balun, to an open wire line, and then to the antenna. All right. Back in the day, Count Zeppelin in Friedrichshafen had a problem. He was building Zeppelins, and the lighter-than-air ships in Friedrichshafen, and they needed to communicate. And this is, of course, back in the 20s and 30s, and tubes were ruling the day, but they had a problem that they couldn't hang a dipole antenna and feed it at the center because they had no trees to hang the antenna on. What were they to do? Well, they came up with the ZEP antenna, which is an end-fed dipole antenna. And so you can feed it with open wire line, a parallel line, or you can feed it with coax, but it's just an end-fed dipole antenna. Now, the thing is that one half of the antenna is here. The other half happens to be the outside of the coax of the feed line. That will end up radiating as well. But that's a ZEP antenna that could be dragged out the back of an antenna of the Zeppelin, just hanging in the air out there. And remember, this was the tube type days, so they had pi network output transmitters with a very wide impedance matching range. Nowadays, you hear a lot of folks who are doing SOTA or POTA, Parks on the Air, or Summits on the Air, using end-fed wire antennas. But the antennas that we're using today are being fed by solid-state transmitters that don't have that wide pi network output. So typically what we'll have is a transformer that feeds it, a very large 8-to-1 ratio transformer, which will actually be an impedance of about 3,200 ohms at one side, and it may also use a counterpoise off of the transformer to make the end-fed dipole work. This is an end-fed half-wave multiband wire antenna. All right, we have the ZEP. Now we have the extended double ZEP. It's a center-fed 1.25 wavelength antenna. It's actually 2 5/8 wave elements in phase. And it gives you 3 dB gain versus a dipole antenna. So it's much longer of an antenna, but you can feed it at the center with ladder line and then use an antenna tuner with a built-in transformer. But you can actually double your power for free if you've got the real estate to put up an extended double ZEP. It's 2 5/8 wave elements, one going on the left, one going on the right, in phase. We're just moving right along. We're just skimming the surface on antennas. That's all we can do. This is a licensing class. This is not a theory class, but I point that out. All right, vertical antennas. We talked about the vertical quarter wave antennas. You can hang the antenna from a tree. You can actually go up the tree trunk. I've done that as well. And for HF, typically a quarter wavelength high, requiring the radials to mirror the vertical element. Remember to give the radio wave someplace to kick off from. a nice trick, if you can do it, if the antenna doesn't have to be too long, is if you can take the feed point of the antenna up off the ground and elevate it. And when you do that here on the right, that's called an elevated quarter wave vertical antenna. And you can have the radials come from this elevated point and slope downward to the ground. You can get by with just 4 radials in this case. Now, more radials are going to be better, but 4 will give you an adequate performance, and the sloping actually provides some impedance matching. A quarter wave vertical antenna has an impedance half that of a half-wave dipole. So we said the half-wave dipole was 73 ohms. So this is going to be around 36 ohms. But when you slope the radials, it actually comes closer to 50 ohms, a better match for 50 ohm coax. So with an antenna, like the quarter wave vertical, well, what happens when you operate below the resonant frequency of that the antenna was designed? Well, what happens is the radiation resistance, the good R, goes down, and capacitive reactance goes up. We said it's going to be too short. So we say an antenna that's too short is capacitive. So if you operate below the antenna's natural frequency, your radiation resistance, the ability for the antenna to radiate power, is going to go down, and capacitive reactance is going to go up. Well, what to do? What can we do to improve our vertical antenna? We look at the resonant frequency formula. We're not going to have to do this formula right now, but I want to point out that the frequency of resonance of a resonant circuit is equal to 1 over 2 pi times the square root of L in henries and C in farads. L being inductance, C being capacitance. The only thing I want to point out here is that notice 1 over. So every time you increase L or C, the resonant frequency will go down. Increase L or C, and the resonant frequency will go down, or the antenna will look somewhat longer, and that's where we get shortened verticals. And so some vertical antennas you will see will have a coil. The middle is usually the best place if you can put the coil there mechanically. The coil goes in the middle, and you may also then have a capacitance top hat. A capacitance here added to the top in the form of wires or a disc. By adding additional L or C, you can lower the natural resonant frequency of a vertical antenna. By adding the C, you can make this coil smaller because you don't need as big a coil. That reduces the resistance losses in the coil, the R, the bad R, through the coil. So we say that capacitive loading improves the antenna's radiation efficiency because you can actually lower you can make the coil smaller. Excuse me. That was kind of convoluted, but I hope you got that. Sorry. All right, for mobile antennas, we talked about these before. You know, we want a large gauge wire wrapped in coils. We want to reduce the resistance as much as possible to get the bad R out of the equation. And we desire the ratio of the reactance to resistance to be high. We want it to be inductively reactive to make it look electrically longer, but we want the resistance, the bad R, to be low. So that's why we have high Q loading coils. The larger coils minimize the ohmic losses and heating. All right, Gary, I've got limited space. I can only put up a very small Yagi antenna. Well, like this one, for example. Here's a 2-element Yagi antenna, probably for 6 meters, although I don't know exactly the size. Well, how can I improve my my performance when I don't have a lot of extra room? I don't have room where I can have a longer boom with more elements. Well, you can stack antennas. You can put 2 over 2. You'll get a 3 dB gain because you've got two antennas working together, and because they interact with each other, you'll get a lower angle of radiation, and you'll get improved performance. In fact, this very array sits just outside the studio here. The guys couldn't see it tonight, it's raining so hard, but it's my new field day antennas for 6 meters for our upcoming field day in June. 2/2 on a rotatable mast. Getting fancy this year. So I'm feeding the antennas with 2 equal lengths of feed line. But you can actually change these lengths depending on what you want to do, and you can use computers to model the antennas. But phasing lines, that's what they're called, it ensures that each driven element operates in concert with the others to create a desired antenna pattern. That's what phasing lines are all about. And so if you've got a 50 ohm antenna out here, all right, presenting 50 ohms here at this point, 50 ohms presenting 50 ohms here, 50 in parallel with 50 is going to be 25 ohms at this point. And that's going to be a mismatch. It's going to be a standing wave ratio of 2:1. Okay, that might be okay. Your radio might be able to tolerate that, or you might be able to use an antenna tuner, or you could use something like this, the Wilkinson divider. It's a power divider circuit that can achieve isolation between the output ports while maintaining a match condition on all ports. And here's links to the Wilkinson divider with more details. One characteristic is there's a small resistor, an equalizing resistor that's added at the output. And you can see it here, it's an SMD resistor. And this gives you 50 ohms in, and then 50 ohms and 50 ohms. So you have a perfect impedance match, and you don't have an impedance mismatch, so there's no reflective power. We'll talk a lot more about that next week. There are other ways of impedance matching. I just want you to know about that you can use an RF transformer, for example, or you can use what they call lumped constants or an L network with inductors or capacitors, or you can use a quarter wave transmission line transformer. And I'm going to show you an example of that next week as well. And if you want to learn more about these lumped constants for impedance matching, I went overboard. I've got 3 websites here you can investigate where you can do some online calculations to calculate the values of components to do impedance matching. So if you're faced with this problem, you can actually use these to determine impedance matching. So it's important when you're putting 2 antennas together, and it could be the 2/2 like you saw there, or it could be an antenna like this. So here in the United States, this might be a medium wave broadcast tower on AM, but the FCC sometimes will give broadcasters the restriction that they have to make a directional pattern to protect an adjacent station that is nearby. And so then they have to come up with a directional antenna pattern. The simplest is with 2 vertical towers. And by changing the phasing lines, by changing the distance of the antennas away from each other, you can have different antenna patterns. And if we look on page 9-18 in your book, you'll find this diagram. I'm sorry that it's kind of crooked here, but these, right from the National Association of Broadcasters engineering manual, the same thing is how they did directional patterns for medium wave broadcast. And for us, they'd like us to consider 3 cases of quarter wave vertical antennas spaced apart a certain distance and fed in a certain way with phasing lines. So let's, condition number 1, quarter wave vertical antennas that are spaced a half of a wavelength apart and fed in phase. And the result is a figure 8 pattern that is broadside to the axis of the array. So here's one tower, we're looking down on top of it. Here's one tower, here's the other tower. They're a half of a wavelength apart, and they're fed in phase, so the pattern is going to be a figure 8 broadside to the array. So all right, here's your visual cue. In phase, when the guns on a battleship are fired at the same time, it gives you a broadside. In phase gives you a broadside. All right? Here's condition number 2. Quarter wave vertical antennas, again a half wavelength apart, but fed 180 degrees out of phase. This results in a figure 8 pattern again, but now it's along the axis of the antennas. So out of phase gives you an on-axis figure 8 pattern. Ooh, now I have to apologize to my German viewer. I apologize for my... Okay, we said, from a Western point of view, the axis was out of phase with the rest of the world. Going back to World War II. But I want to put these as memory hooks. The axis was out of phase. So it's on the axis of the towers. All right, final, this is more loving, spaced a quarter wavelength apart and fed 90 degrees out of phase, it results in a cardioid pattern. So it's got a significant null right here, and then the rest of the pattern goes in this direction. This null was important to the FCC here in the United States because let's say you had another station you were trying to protect down here, your energy wouldn't go and interfere with them. So that's why this was popular. So 90 degrees equals a cardioid or heart-shaped pattern. So 90 degrees has my heart. So half wave fed in phase gives you a pattern broadside. Half wave length apart fed out of phase along the axis, and quarter wave apart is 90 degrees. And if you want to learn the real details of how to coordinate two fed vertical antennas for amateur radio, I highly recommend this YouTube video, A Practical Guide to Tuning a Parasitic Antenna by a Canadian ham, Steve, I believe. And he does a great job of indicating how he does it. He has a directional array, I think, on 160 meters. Sorry, long wire antennas. Just know that as the antenna gets longer and longer and longer, the lobes of the pattern align more closely with the direction of the wire, which is why a longer long wire antenna is more directional. Well, I'm losing my voice tonight. All right. This is my favorite antenna. I've got two of them up here on the homestead. Off-center fed dipoles. They're sometimes called Windom antennas, but that's kind of a misnomer, but okay. It's a multi-band antenna. It requires a 4-to-1 or a 6-to-1 balun at the feed point. So with a normal dipole antenna that's a half wavelength long, you feed at the center, and this is the low impedance point. Whereas, and so one half of the antenna is over here, one half of the antenna is over here, okay? With a off-center fed, typically it's 2/3 of the antenna, then you feed point, and 1/3 of the antenna. So with a classically fed Windom antenna using a current balun right here, the feed point impedance is typically around 200 to 300 ohms. A balun here will give you a good match to 50 ohm coax, and you can use the fundamental band for which it was designed. So if this was an 80 meter dipole, it would be about 130 feet long. You can use it on 80 meters, no problem. Here, in fact, there's the current distribution on an 80 meter half-wave dipole. We said the current is going to be highest at the center. This is going to be the low impedance point because the ratio of voltage to current is such. This is the low impedance point. The high impedance point is going to be at the ends. Well, here we're someplace in the middle. And here's some various points where you can feed the antenna for 80-meter operation. Cool. Well, if you wanted to use an 80-meter antenna, half-wave dipole, on 40 meters, you'll find you can't feed it at the center. If you feed it at the center, this is useless because it won't accept any power because of the dimensions. However, if you feed this antenna on 40 meters as an off-center fed dipole, it will accept power and radiate. Oh, so we can use it on 40 meters too. And we can use it on 30 meters, and we can use it on 20 meters, and we can use it on 17 meters, and we can use it on 15, and we can use it on 10. Now, it'll work better on some bands than others, and not all of these are guaranteed. But the off-center fed dipole, or Windom antenna, is a great multi-band antenna that you can use and to get on the air with the minimum of fuss. I wanted to point out that there is something called the Carolina Windom. This is actually a marketing term, but it's an off-center fed dipole, 50 feet on one side, 83 on the other, which uses a 22-foot long coax and a one-to-one balun here, or an unbalun. This radiates, the vertical element radiates, this radiates, and this is a voltage balun as opposed to a current balun for the Carolina Windom. Not as popular, but they are out there, and I just wanted to define that for you. But off-center fed dipole antennas, I've got 2 of them, and they work great. When I worked for Voice of America, curtain antennas were the big antennas that we used, but we also used rhombic antennas. Curtain antennas have a gain of about 20 dB. Rhombic antennas have a gain of about 15 dB, and they'll work over an entire octave of frequencies. So if the lowest frequency is 6 megahertz, it'll also work up to 12 megahertz, so the next octave. So it's a wideband antenna, and you feed it with open wire feeder on one side. It comes up, these are very large antennas, and at the opposite end, if you leave it unterminated, it's a bidirectional antenna. But if you run feed line down, and then we use nichrome wire laced on the ground to the point where it would do an impedance match, it made it a unidirectional or a single direction antenna. That's a rhombic antenna with 15 dB of gain. Really cool. If you got the real estate and you can put them up, they work great. Satellite antennas are another directional antenna. They focus RF energy at a feed point. The thing we want you to know about parabolic dish antennas, they're good for UHF and up. They're high gain, can be up to 50 dBi, and the gain varies by the square of the frequency. So if you're going to use the same dish, but you double the frequency, you get an additional 6 dB of gain, or 4 times gain. So gain varies by the square of the frequency with a parabolic dish antenna. Just be aware of that. And all of this is coming from the focusing and the phasing of the radio waves together. We do that also with Yagi antennas as well. Yagi for HF and VHF and UHF, directional antennas. They're linearly polarized, horizontal or vertical. Remember, corresponds to the electric field of the antenna. And you can have a driven element, which is a half-wave dipole. You can have a reflector element. In this case, we've got 2 director elements, and they mutually couple together and creating constructive and destructive interference and making the antenna directional. And it's all about wave reinforcement. Again, we're not going to get really deep into it, but the longer reflector element shifts the reflection slightly to enhance directivity, and element length is fine-tuning in the control of the phase shift in a Yagi antenna. And as I mentioned, the driven element of a Yagi antenna is typically a half-wave dipole antenna. So if it's for 20 meters, it's going to be about 10 meters long. This is something I hadn't thought about, but a 2-element Yagi with a reflector has higher gain than one with just a director. So if you have a driven element and a reflector, that's better than a driven element and a director, which is the reason why you see hex beams with reflector elements, because they have a higher gain. And so a hex beam is just a two-element Yagi with the elements kind of bent around, but a very effective antenna. I have one of these as well. And if you want to learn more about how two-element Yagi might be adjusted as a parasitic array, again, Steve has another video here on YouTube with much more detail and much more depth. So we said that Yagi antennas are linear antennas, or horizontal or vertical polarized, but you can get circular polarization from Yagi antennas with two Yagis mounted perpendicular to each other and fed 90 degrees out of phase using a phasing line. This is typically used for amateur satellites. So that's circular polarization using Yagi antennas. So if we go down in frequency, down to the low band, 160 meters and even 80 meters, we're more interested now in receiving antennas. Atmospheric noise is so high at these lower frequencies that antenna gain is not as important as dealing with the noise. And there's this chart, and I got this from the Flex Radio reflector, where they'd added some S-unit markings here over on the side. But if we look here, this is frequency in megahertz. So here's 160 meters and here's 80 meters. The noise levels are much higher down here, and here we have rural, quiet rural and residential areas. You go into a more populated area, the noise is going to go up. So we're looking to maybe put up antennas designed just for reception of high frequency signals. And when we do that, we deal with something called the receive directivity factor. And also known as the noise improvement factor. It's a figure of merit for radio receiving antennas, and it's defined as the gain in the forward direction, or the main lobe, divided by the gain in all other directions of a hemisphere. So I liken it as to kind of half of an isotropic. You're just looking at a hemisphere. This is the standard on which they base. And then you have receive directivity factor. And these are taken from highzantennas.com. They've done an analysis of the various antennas. So here's a top-loaded vertical. It has a receive directivity factor of 5.1 dB because it isn't receiving up here on the top. Now here's our beverage antenna. Look, it's got a receive directivity factor of 11 dB here in the main lobe. All right, that's pretty good. And then we have a K9AY loop and a pennant antenna, both with 7.7 dB of receive directivity factor. So these are figures of merit for receiving antennas. Now our beverage antenna, these are very long, one wavelength or longer antennas, which are known as traveling wave antennas, where radio frequency energy comes from this direction here and goes along the antenna and builds a wave up on the antenna and it goes through a transformer and out to your receiver. This is a traveling wave antenna with the resistor here that makes it a unidirectional antenna. So it's only going to receive signals from this direction and be immune to signals coming from the other direction. So this is a beverage antenna. By definition, it's one or more wavelengths long. Of course, I'm going to contradict that here in just a second, but I just wanted you to know about that. Did you know that you can use your antenna analyzer with your beverage antenna to determine the optimum resistor value here? You can determine the best value of R by sweeping with your antenna analyzer over the bandwidth that you want to receive, let's say 160 and 80 meters, and you're looking for the minimum SWR variation over this desired bandwidth. So you can put in a 450 ohm resistor, which is the typical standard, but you can also put a 300 ohm resistor and see if the variations get better. So you can determine for your case. Again, you want to have a ground rod here, and radials are also desirable here at the ends of the Beveridge antenna. All right. Beveridge antennas, by definition, and what I want you to remember, they're one wavelength or longer. Of course, Gary Breed, K9AY, the guy who designed the K9AY triangle antenna, he did a paper on short Beveridge antennas. And the URL there is in the middle. And antennas that are about 135 feet long actually do have these particular characteristics, directional characteristics. I've got 2 of these up here at my QTH, and they are valuable additions to my arsenal for receiving on 160 and 80 meters. Now, if you got some real estate and you don't mind putting up something in your backyard that your neighbors might love, here's a Waller flag antenna. We know somebody, K4SV, Dave Anderson, who's got one of these in his backyard. Wow. But it's a directional antenna. It's 2 electrically small terminated loops, and they're phased end fire. It's in the plane of the antenna. And then pennant antennas have a cardioid pattern, which are kind of handy because you can find the direction of the signals coming in. So these are low noise receiving antennas for the low bands. And just receiving loop antennas are popular. They can be as simple as a wire that you wrap around a wooden frame. 1 or more turns of wire wound in the shape of a large open coil gives you a receiving loop antenna. And the output voltage is directly proportional to the number of turns and the area of the structure. So more turns are better, and bigger is better for a receiving loop. And you can take this one step further and shield the loop. Then when you do that, by shielding it, it responds only to magnetic fields. It's then electrostatically balanced against ground, and it gives you better nulls. But with all of these antennas, they're bidirectional in the plane of the antenna. So this antenna would be directional in to the left or to the right. Does anybody have Netflix here in the United States? There's a great movie that's on Netflix right now, Midway, which talks about the experience of the Navy, U.S. Navy in World War II in the Pacific. And this very topic is part of the movie. The British used to call it HFDUF, high frequency direction finding. And they used loop antennas, which were bidirectional, remember, and the problem with a loop antenna like they might have on top of a ship is you didn't know which way the signal was coming from. Was it coming from the left or was it coming from the right? You couldn't be sure. And so you find in the movie, the Midway, they made a guess and they went the wrong way because they didn't have enough information. The loop antennas are bidirectional, and so later engineers developed something called a sense antenna, which can be added to a loop antenna system to make it unidirectional. It adds a null in one direction. And so for aircraft that use directional loops, for example, they always have a sense antenna added. Another way they could have found the location of the transmissions better would be if they could triangulate. If they had 2 loops at different locations and they could determine the line of the signal, well then from both locations, then you could triangulate and find the transmitter. That's another way to use that. And always in direction finding, don't overload your receiver. Make sure that you have an attenuator ahead of it because you don't want to get false peaks. And that antenna with a cardioid pattern, like the pennant antennas, the null of that antenna is actually more important than the high gain. If you can point the null at the location where you think the transmitter is and the signal goes away, then you can be assured that that's the direction of the transmitter. So very useful for direction finding. Oh, you made it, guys. Congratulations, guys and gals. All right, let's answer some questions, and then I'll send you home. All right. What type of radiation pattern is created by two quarter wavelength vertical antennas spaced a half wavelength apart and fed out of phase?
Delta.
Yes, out of phase is along the axis of the array. And what type of radiation pattern is created by two quarter wavelength vertical antennas spaced a quarter wavelength apart and fed 90 degrees out of phase?
Alpha.
It is alpha. That's the heart shape or cardioid pattern. And what type of radiation pattern is created by two quarter wavelength vertical antennas spaced a half wavelength apart and fed in phase? In phase?
Charlie.
Gives a broadside when the guns go off at the same time. That's a broadside. So what happens to the radiation pattern of an unterminated long wire antenna as the wire length is increased?
Bravo.
It is Bravo. The additional lobes form with major lobes increasingly aligned with the axis of the antenna.
That is puzzling.
but it's required for the test, so okay. What is the purpose of feeding an off-center fed dipole between the center and one end instead of at the midpoint?
Alpha.
Yep, to create similar feed point impedances on multiple bands. And what is the effect of adding a terminating resistor to a rhombic or long wire antenna?
Bravo.
Yeah, it changes the radiation pattern from bidirectional to unidirectional. And what is the approximate feed point impedance at the center of a two-wire half-wave folded dipole antenna?
Alpha.
Alpha.
You make it with 300 ohm coax and you feed it with 300 ohm coax. Yep. And what is a folded dipole antenna?
Charlie.
Yeah, I don't like this, but okay. It's a half-wave dipole with an additional parallel wire connecting its two ends. It's a loop, a very thin loop. Okay. So which of the following describes a G5RV antenna?
Alpha.
Yeah, it's a wire antenna center fed through a specific length of open wire line connected to a ballon and then coaxial feed line. That's a G5RV. And which of the following describes a ZEP antenna?
Bravo.
Yeah, they dragged it out the back of the Zeppelin. It's an end-fed half-wave dipole. And which of the following describes an extended double ZEP antenna?
Charlie.
Yep, it's a center-fed 1.25 wavelength dipole antenna, giving you 3 dB of gain over a standard half-wave. And how much does the gain of an ideal parabolic reflector antenna increase when the operating frequency is doubled?
Delta.
Gain varies by the square of the frequency. So if you double the frequency, gain is going to go up 4 times, or 6 dB. So how can 2 linearly polarized Yagi antennas be used to produce circular polarization?
Charlie.
Charlie.
Yep. Arrange 2 Yagis on the same axis and perpendicular to each other, with the driven elements at the same point on the boom and fed using phasing lines 90 degrees out of phase. And what is the most efficient location for a loading coil on an electrically short whip?
Alpha.
Alpha.
Yeah, you want it near the center if you can. Now, mechanically, it may not be possible. So why should an antenna loading coils have a high ratio of reactance to resistance?
Charlie.
Charlie.
Yep, to maximize radiation efficiency. You want not a lot of bad R. All right, approximately how long is a Yagi's driven element?
How about delta?
Yeah, usually it's a half-wave dipole. And what happens to SWR bandwidth when 1 or more loading coils are used to resonate an electrically short antenna?
Baker.
It is decreased. Yes, you're making it a higher Q antenna, so the SWR bandwidth goes down. And what is an advantage of top loading an electrically short HF vertical antenna? This is by adding capacitance at the top of an antenna through wires or a top hat.
Delta.
It does. It improves radiation efficiency through the use of then a smaller coil. It's going a long way around the barn, but that's the answer. So what is the function of a loading coil in an electrically short antenna?
Delta.
Yes, to resonate the antenna by canceling the capacitive reactance of a shorter antenna. All right, how does radiation resistance of a base-fed whip antenna change below its resonant frequency? So if you go down below its normal resonant frequency, what happens?
Baker.
Yeah, radiation resistance will decrease and capacitive reactance will increase. So why do most 2-element Yagis with normal spacing have a reflector instead of a director?
Delta.
Yep, higher gain. That's why the hex beam has a reflector. And what is the purpose of making a Yagi's parasitic elements either longer or shorter than resonance?
Charlie.
It is the control of the phase shift that then causes constructive and deconstructive waves, yes. And what is the use for a Wilkinson divider?
Charlie.
Yep, to divide power equally between 250 ohm loads while maintaining 50 ohm input impedance. And what is the purpose of using multiple driven elements connected through phasing lines?
Alpha.
Alpha.
Yes, you will control the antenna's radiation pattern. The phasing lines are a part of that. And when constructing a beverage antenna, which of the following factors should be included in the design to achieve good performance at the desired frequency?
Baker.
Delta.
Delta. It should be at least 1 wavelength long. And which is generally true for 160 and 80 meter receiving antennas?
Alpha.
Yeah, atmospheric noise is so high that directivity is more important than losses. We don't care about the gain of receiving antennas that much for the low bands. All right, what is receiving directivity factor?
Delta.
Delta, remember we saw the hemisphere, the half anisotropic, yeah, it's peak antenna gain compared to the average gain over the hemisphere around or above the antenna. And what is the purpose of placing an electrostatic shield around a small loop direction finding antenna?
Baker.
Yep, it eliminates unbalanced capacitive coupling to the antenna's surroundings, which improves the depth of its nulls. So what challenge is presented by a small wire loop antenna for direction finding?
Alpha.
You could go the wrong way. It's got a bidirectional null pattern. And what indicates the correct value of terminating resistance for a beverage antenna?
Is it delta?
It is. You can hook your antenna analyzer to the input of the antenna and then look at the readout and the minimum variation in standing wave ratio over the desired frequency range. It gives you the best value for the resistor. All right, what is the function of a beverage antenna's termination resistor?
Baker.
Yeah, it does. It absorbs signals from the reverse direction, making the antenna unidirectional. And what is the function of a sense antenna?
Alpha.
Yeah, it modifies the pattern of a direction-finding antenna to provide a null in only one direction. And what type of radiation pattern is created by a single-turn terminated loop, such as a pennant antenna?
Alpha.
Yeah, I gave you the heart symbol there. It's cardioid. And how can the output voltage of a multiple turn receiving loop antenna be increased?
Charlie.
Yep, by increasing the number of turns and or the area enclosed by the loop. And what feature of a cardioid pattern antenna makes it useful for direction finding?
Baker.
Baker.
Yeah, it has a single null. And that's great. And we made it to the end of Chapter 9, Part 1. But wait, I've got some homework for you. Although you'll find it fun and interesting homework. So I'll be sending you this URL to the YouTube video of Ham Radio Now videocast. It's called Standing Up for Standing Waves. It's a great presentation. It's about 90 minutes long, but you'll see some stuff there and you'll go, oh, that's what that means. So I think you will like it. And then don't go to this next location on YouTube unless you have some extra time. But the physics videos by Eugene Kurtyansky are just amazing. And I've asked him if I could use his videos in our classes, and he said no. So you have to go to his channel. But he's got great videos that explain a lot of things about electronics, shielding, grounding, transmission lines, antennas. You'll love them. All right, keep calm and go home. Oh wait, you're already home. Oh, we made it in under 2 hours. That is unbelievable. Are there any comments or questions from anyone? We can go ahead and remove the spotlight if you want, Dave.
Finish reading 9.4 transmission lines.
Yeah, so we'll finish up the rest of chapter 9 for next week. Yes. So 9.3, 9.4, 9.5, whatever sections are left. And we will introduce you to the cult of the Smith chart next week. All right. Take a break. Calm down. You did great tonight. There's a lot of information here, and I really appreciate you all. Dave, did you have any final thoughts?
No, not here. It's just a lot of things to absorb, and Gary focused on what you need to know for the pool questions, and the links, if you have time, are just incredibly valuable if you want to dig deeper.
Great. All right, y'all. It's raining hard here. We're going to get wet on the way home. You keep dry. Take care. 73, and we will see y'all next week.
3.
73. Thank you. 73.